Hello everyone, my name is Neno Toric. I'm an associate professor working at the Faculty of Civil Engineering, Architecture and Geodesy, and today I'm going to present a paper titled Rheological Modeling of High Temperature Stationary Creep Tests on Grade S275JR steel. So why do we have to think about rheological modeling of steel in the first place? So if we imagine a steel structure which is exposed to fire at a certain point, there are two end possibilities for development of heating rates in each of its constitutive members that is possible. So if we consider a general heating curve which has a cooling phase occurring at certain point, the first possibility is that the steel member is going to have very high heating rates induced because there isn't any fire protection present, or in the case if there is any fire protection present, there's going to be a very low heating rate possibility in that particular steel member. So the main question is, does this heating rate development, which can vary from very high to very low, can affect the load bearing capacity of that particular steel member? So the same applies to columns, beams, and connections, which are constitutive parts of the structure itself. The main components in fire-affected steel are basically composed of three parts. So today's topics are related to stress-related strain and the creep strain. So the stress-related strain, or a mechanical strain as it is called, can be determined by using either constant temperature or transient testing procedure. So if we are using a constant temperature testing procedure, we generally get information about the mechanical property of steel at high temperature, for example, yield strength and modulus of elasticity. And if we're conducting transient testing procedure as an output, we can obtain a stress strain law which unifies the mechanical strain and the creep strain in a single stress strain law. So if we do not use the transient testing procedure, we can determine creep strain separately by doing stationary creep tests at constant temperature and at constant stress. So basically, these are the two main test regimes for determining strain components in fire-affected steel. So each of these procedures has its drawbacks, since, for example, transient testing procedure uses a single heating rate, which couples a mechanical strain and a creep strain into a single stress strain law. So basically, it encompasses only creep strain development at that particular heating rate that was used during the tests. The current solution to creep problem is basically given in the form of a unified stress strain law, which obviously unifies mechanical strain and creep strain into a single component. And this stress strain law is widely used in structural fire engineering applications in Europe and over the world. So basically, if we are using this kind of a stress strain law, we cannot obtain any kind of information about the load bearing failure due to heating rate exposure in a general fire event. So this is the main drawback of this kind of a stress strain law, basically. And as a proposal to take into account the heating rate sensitivity of the problem, we are basically offering a solution in the form of a unified rheological model, which can basically model material behavior in a general regime, either if it's exposed to constant temperature or transient temperature, in the form of two Kelvin Voigt elements, which basically give a strain output depending on the strain rate level to which the material is exposed to. So basically, it functions as a two series connections of Kelvin Voigt elements. And the first Kelvin Voigt element takes into account the apparent yield increase in steel due to high strain rate exposure. And the second Kelvin Voigt element takes into account the variability of strain when very low strain rates are present in the steel member, namely when creep occurs, basically. And if we have constitutive components which are strain rate sensitive and heat rate sensitive, then basically we can model material behavior at any heating rate present during the fire. So a general form of a unified rheological model has been proposed in a research paper in 2016 by the authors of this paper. And basically, in that paper, there's an analytical procedure how the general model functions in terms of solving the differential equations for Kelvin Voigt elements. So in general terms, the stress in the spring and the damper element is temperature and stress sensitive when it comes to springs, and when it comes to dampers, the constitutive models for the dampers are strain rate and temperature sensitive, which takes into account all the variables that are changing during a general fire event. The stress rate solver, the schematics is presented in this slide. So generally, a different procedure is employed for solving the differential equations for the Kelvin Voigt elements. If, for example, we are having a strain rate control problem, so the calculation procedure is a bit different. So this paper relates to station and creep tests. So basically, it's a stress-related issue for solving. So this is the procedure how to calculate the stress levels in spring and damper components for each element, the procedure for it. And in the figure below, it is presented how stress varies in the damper and the spring element with respect to time in a general stationary creep test, which is modeled in the next slide. So this is an ongoing research in terms of further development of the unified rheological model. So this is the comparison taken from Grade S275JR study, which was conducted previously at 400 degrees temperature. So this is a graph that shows a simulation of stationary creep tests conducted at different stress levels. So you can see that the unified rheological model can create a strain output which is comparable to the stationary creep tests that were used for verification of the model for modeling stationary creep tests. These are the results which are presented for another grade. This is the grade S355, and the results are presented for the temperature of 400 degrees as well. So we can see that the model can provide a reasonable strain output, which is comparable to the strain developed at stationary creep tests for this particular steel alloy. So this is an ongoing research, and the current presentation only relates to 400 degrees, and we will conduct further modelings at temperatures higher than 400 degrees. So as a short conclusion, so this unified rheological model takes into account strict variation and the heat rate dependent creep strain. This wasn't visible because we are at this stage we are trying to model stationary creep tests, so there is no heating rate variation because the temperature is constant. But it is sensitive to variable strain and heating rate because we tested it previously on different transient constant temperature studies. And the constitutive model parameters, which are presented in the research papers, but not in this presentation, seem applicable for modeling European steel grades 275 and 355, as it was presented in the previous slides. And the current development stage is to test the performance of the unified rheologic model and modeling stationary creep tests as it was presented by the previous slides. Also, in case you're interested in researching time-dependent behavior of steel structures or metallic structures in general, which are exposed to fire, in case you have some interesting research paper that you can share, which is similar to the research presented here, there is a special issue currently open in Journal of Crystals, which I'm co-authoring as a guest editor with my colleagues, Professor Tomasz Hozian and Dr. Mohamed Ali Morat and Professor Michael Ehnhardt. So in case you're interested in publishing some kind of research paper which is related to this topic, you are more than open to submit it to this special issue. I would like to thank you for your attention. I hope that this presentation was interesting, and I'd be happy to answer any of your questions if they are present. Thank you.